Hello, I'm Chris Mack, and the title of this presentation is Probabilistic Process Window, a New Approach to Focus Exposure Analysis. This is a talk that I first gave at the 2022 Advanced Lithography and Patterning Conference. My co-authors, Jonathan Yanuzzi of Fractilia, did much of the algorithm work behind the Probabilistic Process Window, and my co-authors, co-workers, and friends at IMEC provided much of the experimental data we use to validate this approach. Process window metrology is very important in the field of semiconductor lithography. The two main purposes. First is to determine the process window size, to figure out what the depth of focus is at a particular exposure latitude spec, for example. This enables us to choose between processes, material A, material B, pick which source shape will provide the best results in lithography, optimize processes in general. But it's also used to determine best dose and best focus for our scanner. We use that, of course, in R&D, but especially in high-volume manufacturing, centering your process in the middle of the process window is critical to getting the maximum yield out of your lithography process. But as process window sizes continue to shrink with every new generation of feature size, this has a noticeable impact on our abilities to both measure the size of the process window and to determine best dose and best focus, which is even more critical with small process windows. So how do we do this? How do we determine the size of the process window and best dose, best focus? Well, historically, we've used something called the geometric process window approach. I did a lot of work in the 90s to develop the way we do this today, wrote some software still in use today, back in those days, to determine process window size and best dose and best focus. And 4 steps go something like this. First, we take our data and we fit it to some kind of a function, usually a particular polynomial style function. And we do that in order to smooth the data and reduce the impact of noise in the data, because none of our data is perfect. So we fit our functions, usually CD, but sometimes other variables as well, and smooth it out. Then we take the output of that function and plot it as a contour plot. This allows us to define the specific specs of interest as contours. If we have more than one spec or more than one feature, we overlap those contours and find a geometric region that meets all the spec. We call that the process window. Finally, we fit maximal rectangles or ellipses inside this process window and generate our exposure latitude versus depth of focus curve. So the first step, and we'll go through a few of these steps to describe some of the problems associated. The first step is fitting the data to some kind of a mathematical function. Here are some papers in the 90s describing, and early 2000s describing how to do that in optimal ways. One of the questions we have is, what is the best function to use? And in particular for polynomials, the right order of the polynomial to use. It's a bit of an arbitrary choice, and by making changes to these choices, we change our results. We get different process windows depending on the order of a dose or focus we use. We don't know what the optimal order is or even the optimal function, and therefore there's a certain arbitrariness to the size and shape of the process window that results. In step 2, we create these contours, and then we basically say that inside the process window we have success, outside failure. So binary function 0 or 1, you're either in or out of the process window. And the contour is interpreted as a sharp line, an exact cutoff between inside and outside the process window. But this sharp boundary does not take into account metrology uncertainty. In reality, we don't know exactly where that boundary is, but we don't take any information about that uncertainty into account. The last step, after we've overlapped some specs, so here's a few specs being overlapped together, the last step will be to fit either a rectangle or an ellipse inside that process window and find the maximum size maximum width for every given height, for example. And that produces the exposure latitude versus depth of focus curve. The ellipse method is used for random errors, and the rectangle method is used for systematic errors. The problem with this geometric approach to sizing inside the process window is that these shapes will hit the process window at only a few points. In this particular case, it's hitting it at exactly 3 points. Only these 3 points determine maximal ellipse or rectangle that fits inside the process window. That makes it very sensitive to a couple of points and completely insensitive to the whole rest of the shape of the process window. Well, something doesn't feel right about that. It seems a little bit too sensitive to a few points. And I'll talk about a different approach that eliminates this sensitivity as well. So I've outlined a few problems that exist with the geometric approach to process window metrology. What I'd like to do now is propose a new approach, which I call the probabilistic process window. It takes place in 3 steps, and I'll go through these 3 steps in a little bit more detail in the coming slides. We begin by taking our data of, say, dose and focus with CD as an output. We ask the question, at any given dose and focus setting, what is the probability that the resulting features meet all the specs? Now, if you do not take uncertainty into account, well, then the probability is either 0 or 1, and we get the same result as the geometric process window. But when we do take metrology uncertainty into account, we may get something that's a probability between 0 and 1. That's what we call the probabilistic process window. It's a plot of the probability of meeting every spec that you have as a function of dose and focus. Then we're going to measure the size of this probabilistic process window probabilistically. We will assume that dose and focus are set at a particular value, but then around that dose and focus setting, there are errors in our process. Cross field, cross wafer, whatever they might be, we have a Gaussian distribution of dose and focus errors that exist in real life on our wafer. So, given this Gaussian distribution centered at a particular point, we ask ourselves, and we perform the calculation, what are the fraction of features that meet all specifications? We do this for every single dose and focus value. The best dose and focus are going to be means of that distribution that produce the maximum fraction of features meeting spec, because after all, that's what we really want on the wafer, the maximum of features printed on our wafer that meet specs. Then we repeat that process for differing amounts of 6 sigma process errors, plus or minus 3 sigma process errors. We do this repeatedly, and we look for the range of process errors that produce exactly 99.73% of features meeting specs. Well, that's just the Gaussian cutoff for a plus or minus 3 sigma of the features that meet spec, which is our typical way of speccing things. By doing this over and over again, we generate the exposure latitude versus depth of focus curve. All right, what's the difference? Step 1 of the probabilistic process window. Here I've got 2 specs, CD and the unbiased LWR, find an overlapping process window shown here. Again, 0 or 1, we're either inside or out, but when we take metrology uncertainty into account, we see that we have 0 probability out here, probability of about 1 inside, and the edges are fuzzy. They're not sharp. There's a fall off in probability as we approach the edges of the process window because of metrology uncertainty. If we look a little bit closer at, say, this corner, we can see these probabilities at work. So it really is about 0 when we're a long ways from the edge. It's about 1. We're right in the middle of the process window, but near the edge, we have this kind of gradual fall off, and we see probabilities of 54% or 10% or 66% at various dose and focus settings. this gradual fall off is due to measurement uncertainty. So we've solved the problem of not taking measurement uncertainty into account. The next step of the probabilistic process window would be to take every mean dose value, mean focus value, and apply some Six Sigma process error. So pick a value of how much errors in focus you have, how much errors in dose you have, and then calculate the fraction of features that meet all the specifications. We do that again for every setting of dose and focus, and we get this fraction of inspect feature plot. The point at which we get the maximum fraction of inspect features is how we would define the most logical way possible the best dose and focus values. But these Six Sigma errors can be varied as well, so we can do this repeatedly. If we set the range of Six Sigma errors in focus to be a certain value, our depth of focus, and then we vary the range and mean dose and mean focus for dose, we can determine what exposure latitude would produce exactly 99.3% of features being in spec at best dose and best focus. This produces a curve called the exposure latitude versus depth of focus curve, just like we get from our geometric process window approach, but now we're taking into account the entire process window shape. All of the data contributing to our understanding of the fraction of features on the wafer that are going to meet spec. This provides a more accurate, rigorous assessment of exposure latitude and depth of focus. Here I set the exposure latitude to be 10% of the nominal exposure. We get a best dose, a best focus, and a depth of focus, all determined in this rigorous probabilistic way. So the advantages of the probabilistic process window. Number one, I didn't really emphasize much so far, was that we can integrate CD with any other specifications trivially. If we have stochastic specifications like unbiased LWR, we could have a line wiggling spec, we could have any spec we want, defectivity. It's easy to add any other spec because the probabilities simply multiply. The probability of getting meeting one spec versus another versus another. There are no arbitrary fitting functions that are used. It takes metrology error fully into account without any kind of smoothing that we might get from these fitting functions. And our determination of process window size is much more rigorous because it's not just looking at the outside of a Gaussian 3 sigma shape like an ellipse, and it doesn't worry about specific points touching specific contours, but instead uses the entire data set to perform the most rigorous calculation of the fraction of inspect features that we would expect on our wafer. Here's some example data. This was collected at IMEC on ADI wafer with 3 different pitches, standard metrology settings as used at IMEC. We have 1 image per dose focus value, and all the measurements were made with the latest version of Metrology for the probabilistic process window calculation. Here's the data for pitch 32, and here's the process window. In this case, we use 2 specs, the CD and the unbiased LWR. And interestingly, our unbiased LWR spec ends up being the limiter to the range of focus, and even in the underexposed case, it's the LWR, not the CD spec, just in this case, that is causing the limit. As is often occurs, the focus range is cut off left and right, high and low extremes of focus, by the LWR. And here's the geometric, here is the probabilistic process window. If we do the same thing for pitch 54 and 80, I'll only show you the geometric process window plots, but we see that, again, the relaxed, in this case, unbiased LWR specs are still cutting off various places, and we see this interesting shift in best focus to more negative values, which meant our range of focus maybe didn't go quite far enough in the negative focus values to capture the full process window. It won't matter because the next step we're going to do is overlap all of these pitch data together. And again, overlapping more and more data sets is still with the probabilistic process window approach, since we simply multiply probabilities together. And when we do that, here is the probabilistic process window overlapping for every one of these pitches. Now, I'm plotting all the contours as well. That's just for reference, just for visualization, because in fact, none of these contours are used for any of the calculations in the probabilistic process window. Only the probabilities themselves, as shown in the heat map plot here. Again, we're limited by multiple specs of CD, different pitches, and also LWRs for different pitches, end up overlapping and producing the final probability. Here's the process window size, exposure latitude versus depth of focus, with the determined best dose and best focus. As a final example, I'd like to show you the extreme difference you get when you include or do not include LWR specs. It's quite common because it's pretty easy to measure CD in fabs that we only use CD specs. Well, you get a very different result if you include LWR specs as well. LWR ends up being quite the limiter to focus in many cases, and without that we miss where we should center our process window. If we do care about LWR or other stochastic specs, we need to. In this case, the depth of focus estimate increased by 50% when the LWR specs were removed. So in conclusion, the traditional geometric process window approach has several limitations. Measurement uncertainty is not taken into account. We use these arbitrary fitting functions to deal with our noisy data, and differences in results based on what fitting function we use are inevitable. The geometric fitting of a shape into the process window makes the determination of depth of focus, best dose, best focus, dependent upon how those shapes touch. And those shapes touch the contours at just a few points. And so we're not using the entire set of data effectively. But the new probabilistic process window solves all of these problems based on a rigorous probability theory, taking measurement uncertainty into account, and more accurately reflects behavior on the wafer. So I'm quite confident that the probabilistic process window approach will become the new standard for how to measure, analyze, and use process window data for focus exposure matrices or others, because it's not, in fact, just limited, this approach, just limited to focus and exposure. Thank you very much.